Welcome back, everyone. Today, we're diving straight into an explainer on the absolute bedrock of modern networking. We're going to demystify enterprise campus architecture and the invisible logical shield that keeps it all running, Layer 2 loop prevention. If you've ever stopped to wonder how these massive networks stay up and running without just collapsing in on themselves, well, you're in the exact right place. Let's get into it.
To really wrap our heads around this, we have to look at the sheer scale of the challenge. According to Cisco's annual Internet report, we were projected to hit 29.3 billion networked devices and connections globally by 2023. I mean, 29.3 billion. That's a staggering number. And the kicker? Every single one of those connections demands constant reliability, speed, and uninterrupted access to resources. But it's not just laptops and smartphones anymore, right? The complexity of these networks is absolutely skyrocketing. Get this, a massive 60% of IoT, or Internet of Things devices, now connect using non-Wi-Fi protocols. So we're talking about incredibly diverse, computationally intense traffic pouring into our enterprise environments from literally every direction.
And compounding all of that complexity is the relentless demand for speed. With mobile speeds projected to more than triple, is putting an immense, almost crushing pressure on our underlying network foundations. Without a rock-solid, deeply resilient architecture, that level of scale and speed, it would instantly break a network.
So here's our roadmap for this explainer. We'll start with building the enterprise campus, move through access, distribution, and core, look at the thread of bridging loops, break down spanning tree principles, talk about protecting the topology, and finally wrap up with troubleshooting best practices.
All right, let's kick things off with part 1, building the enterprise campus.
So how do we physically build a network capable of handling billions of connections? Well, you can't just plug switches into each other at random. Unconstrained growth is just a recipe for complete chaos. Instead, the Cisco campus architecture uses a hierarchical network design. It's kind of like building a city. By dividing the network into distinct building blocks, we create what are known as modular fault domains. This is absolutely crucial because if something breaks in one block, that isolation prevents the failure from cascading and taking down your entire enterprise. Moving right along to part 2, access, distribution, and core. Within those building blocks we just talked about, we actually break our enterprise metropolis down into 3 distinct zones. First up is the access layer. Think of this as the edge. It's a feature-rich environment that provides secure connectivity for end users, IP phones, and all those IoT devices. Next, we aggregate those access switches into the distribution layer. This is essentially your boundary zone. It focuses on policy enforcement, quality of service, and shielding the core from high-density problems. And finally, the core layer. This is the campus backbone, and it really only has one job: high-speed packet switching. It's moving traffic as fast as humanly possible across the enterprise.
Now, that brings us to part 3, the threat of bridging loops. Okay, so we've got this beautifully structured physical network, but to ensure high availability, we absolutely need redundant physical links, right? You don't want a single accidentally cut cable taking down an entire building. But here's the catch. In Ethernet, physical redundancy creates loops. And loops, they cause broadcast storms. Think of it like taking a microphone and holding it right up to a speaker until that feedback loops, screeches, and shatters the glass. That data traffic circulates endlessly, chewing up all your bandwidth until the network literally melts down. So how do we actually prevent this?
Let's answer that in part 4, spanning tree protocol principles. To stop that total meltdown, we have to transition from physical hardware to our logical software shield, the spanning tree protocol, or STP. Operating at layer 2, STP is basically an algorithm designed specifically to cut those loops in bridged networks. And it pulls this off by using BPDUs, Bridge Protocol Data Units, as little communication probes. Under normal conditions, assuming all the switches are playing nice, STP dynamically scopes out the physical topology and strategically blocks specific redundant ports. It does this to ensure there's a single, loop-free path for your data. The whole STP topology revolves around a single boss, which we call the root bridge. Every single path is calculated back to this root. But how does a switch get that top job? Well, it's a strict 2-step election process. Step 1, the switch with the lowest bridge priority wins. Simple as that. But what if there's a tie? Step 2, say 2 switches are sitting there with a default priority of 0. In that case, the switch with the lowest MAC address breaks the tie and becomes the root. The golden rule here, the lowest bridge ID always wins. Now, the absolute key here is predictability. You never ever want a random switch winning that election. Thankfully, Cisco gives us tools to automatically lower the priority of our chosen core switches to tightly control this topology. If you configure a switch as the primary route, Cisco automatically drops its priority down to 24,576. If you set a secondary backup route, it drops to 28,672. This perfectly guarantees they are going to beat any standard switch holding that default priority of 32,768. It ensures your traffic flows exactly where you designed it to go. I really want to highlight this golden rule straight from the Cisco documentation. It says the only critical action that STP takes is the blocking of the ports. That's it. Everything else STP does, the BPDUs, the elections, the timers, it's all just in service of deciding exactly which port to block. This really underscores the incredibly high stakes we're dealing with. A single blocking port that mistakenly transitions to forwarding can melt down a massive chunk of your network in a matter of seconds.
Which leads us perfectly into part 5, protecting the topology. Because those stakes are so high, you just can't set up STP and walk away. I mean, imagine someone plugs a rogue switch into a wall port in a conference room, and it suddenly tries to hijack the root bridge status. To stop that cold, we use RootGuard. If a port unexpectedly receives superior BPDUs, RootGuard steps in and places that port into a root-inconsistent blocking state. On the flip side, what if a redundant link has a unidirectional fiber failure and suddenly stops receiving BPDUs? The switch might get confused, unblock its port, and boom, you've got a storm. LoopGuard is designed to detect those missing BPDUs and throw the port into a loop-inconsistent blocking state, stopping the loop before it even starts.
Now, while those features are great for protection, there are others you need to be incredibly careful with. Take BPDU filtering, for example. Consider this a strong warning. Applying BPDU filtering to a switch port effectively disables STP on that port entirely. It just stops sending and receiving BPDUs altogether. It completely blinds the port to the STP topology, which means bridging loops are neither detected nor prevented. So use this only when absolutely necessary and only when you know exactly what is plugged into the other end.
All right, let's wrap this up with part 6, troubleshooting best practices. So, now that we understand the physical hierarchy and the logical STP shield, how do we avoid trouble before it even starts? Well, here are your big takeaways. Number 1, never leave this to plug-and-play chance. Always hard-code your root bridge locations. Take control of it. Number 2, physically map out all your redundant links. You need to know exactly which ports should be blocking in a stable environment. And number 3, tune your design to minimize the total number of blocked ports. Simply put, fewer blocked ports means fewer opportunities for an accidental network meltdown.
And that leaves us with one final thought to ponder. You might have built the absolute perfect physical access, distribution, and core layers. Your network might be hierarchically sound today, but ask yourself this. Is your logical STP topology actively protected against tomorrow's rogue devices or those sudden unexpected link failures? Don't wait for the network to melt down to find out. Take these protective guards and apply them to your enterprise environment immediately. Thanks for hanging out with me on this explainer, and as always, keep learning.